Welcome to the 8th lecture on graph theory. In the first part of this lecture, we learn Hall's theorem. Hall's theorem gives the necessary and sufficient condition for the existence of X saturated matching in bipartite graph. And in the second part of this lecture, we learn vertex cover, and also we will see that the size of maximum matching is equal to the size of minimum vertex cover in bipartite graph. So, let me start with Hall's theorem first. Let G be a bipartite graph of X union Y E. Now, if S is a subset of X, then we define the neighbor of S. The notation for this is NS. NS is equal to set of some vertices in Y such that X Y are adjacent, and for all X in S. So, you take one vertex from the set S and look at its neighbor, and the neighbor of S is union of all such neighbors of different vertices in S. Well, I will give an example to illustrate this notion of neighbor of a set S. Let me consider the same graph that we considered in the previous class. You have a set of 4 girls G1, G2, G3 and G4, and you have a set of 5 boys B1, B2, B3, B4 and B5. Girl 1 or G1 prefers B1, B4 and B5. G2 prefers only B1 and G3 prefers B2, B3 and B4. G4 prefers B2 and B4. Well, now say if I take, so here X is the set of girls G1, G2, G3, G4, and if I take a subset of X, say S is equal to G1 and G2, then the neighbor of S is the union of the neighbor of G1 and the neighbor of G2. So, the neighbor of G1 consists of B1, B4 and B5, B1, B4, B5, and the neighbor of G2 is B1. So, the neighbor of S is this one. let me take another S, say this is another example, say S is equal to G2, G3, G4, and G2 prefers B1, G3 prefers B2, B3, B4, and G4 prefers B2 and B4. So, the neighbor of S is union of all these three things, three sets, that is B1, B2, B3 and B4. So, this is what the neighbor of a set. Now, let me state Hall's theorem, which gives the necessary and sufficient condition for the existence of X saturated matching. A bipartite graph G X union Y E has a matching that saturates X. So, I will explain what is this the meaning of saturates X or X saturated matching. So, a bipartite graph G has a matching that saturates X if and only if this condition is true, that the cardinality of S is less than equal to the cardinality of neighbor of S for all S subset of X. Okay. So, the meaning of this one, first let me say what is X saturated matching. So, if I say this is my X set, X is the set of all girls and Y is the set of all boys, then the meaning of X saturated matching means all the girls are matched. And similarly, the meaning of Y saturated matching is that all the vertices in Y are matched. Now, the conditions say here that you take any subset of girls, say if I take G1 and G2, this is a two subset of the set X, and then I can see that the cardinality of S in this case, it is less than or equal to its neighbor cardinality. That means, the meaning of this one, that these two girls collectively they prefer three boys. Okay. So, that is the meaning of this one, and this should be true for every subset of girls. This condition is very obvious, because if there is a set of say three girls, they collectively prefer say two boys only. That means, there is a set of three girls for which the neighbor set is having only two boys, then you can't find a matching for these three girls. One of these girls will remain unmatched. So, this is a very obvious condition that a set of three girls, or whatever be the number, a set of n girls should collectively prefer at least n boys, and that is what the condition of the Hall's theorem for the existence of a X saturated matching. So, here X is the set of all girls. So, all girls will be matched if and only if any subset of the girl prefer any subset of say k girls prefer at least k boys. So, that is obvious condition for the existence of X saturated matching. Now, you can see that here the number of conditions, how many conditions are there? It says that for all X, for all subset S in X. So, basically you have to check 2 to the power of this many conditions. So, you have to consider all singleton sets and then 2 element subsets, 3 element subsets up to this many the whole X. Okay. So, this many conditions you have to check to see whether there exists a matching X saturated matching or not. Okay, let me give another example to sort of illustrate that, just to explain that this is an example where you will see that the X saturated matching does not exist, because one of the conditions is not satisfied. So, I have this is my X side, and in the Y side again there are 5 vertices. Let me call them 1, 2, 3, 4, and here it is A, B, C, D and E. Now, one is adjacent to B and D, 2 is adjacent to, or the neighbors of 2 are A, C and E. The neighbors of 3 are B and D, and the neighbors of 4 are B and D. Now, the question you have to explain why the graph has no X saturated matching. Sometimes this X saturated matching is also called, instead of saying why the graph has no X saturated matching, one can say why this graph has no perfect matching from X to Y. Well, so that means you have to find some set of this, some subset of this set X for which the Hall's condition is not correct. So, you have to find S, a subset of this 4 vertices for which the cardinality of S is greater than n S. That means a set of say 2 girls or 3 girls, a set of 3 girls for example, they prefer collectively 2 boys only. So, you can't find a perfect matching in that case, and it is not difficult to see in this example that this S could be one, 3, and 4, you can see that S 1 3 4, if this is the set which is subset of the set X, and then you look at the neighbor of S, the neighbor of S, one prefer B and D, B and D, 3 prefers again only B and D, and 4 also prefers only B and D. So, girl 1, 3 and 4, they collectively prefer only B and D. So, then you can't find a perfect matching in this case, because the Hall's condition is sort of violated here. So, so we learned the Hall's condition for the existence of X saturated matching, and I will omit the proof of Hall's theorem. Next, we will talk about several results, and then those results will be proved using the conditions of Hall's theorem. Okay. So, next we talk about one factor of a graph. A graph, a k regular spanning subgraph is called a k factor. So, why I am introducing this definition? Because okay, I want to say that perfect matching is equivalent to one factor. Okay, let me just give an example to illustrate this definition. So, I have defined what is one factor of a graph. Okay. So, it is a spanning subgraph, and it is a k regular spanning subgraph is called k factor of a graph. Suppose you are given this graph, okay. Vertices are A, B, C and D, and you know the meaning of spanning subgraph. A subgraph is said to be spanning if it contains all the vertices of the graph. So, this is a spanning subgraph of the graph G. So, here H is a subgraph of the graph G, and also it is a spanning subgraph. Now, you can see that every vertex of G is having degree 1. So, so H is one regular spanning subgraph. Spanning subgraph of G. So, one can also say that, so telling that H is one regular spanning subgraph of G is same as, this is same as saying that H is a one factor of G. Now, you can see that one factor is a spanning one regular subgraph, and which is same as H is also the edges of the subgraph H. This is a perfect matching basically. So, it matches all the vertices, and so one factor of a graph is basically a perfect matching of that graph. So, a subgraph, sorry, a subgraph H is a one factor of G if and only if the edges of the subgraph is a perfect matching of G. I hope that you understood this one. So, this is one factor of the graph G, and this is also a perfect matching of the graph G. Okay. So, now we will prove a theorem or a result that if G, a bipartite graph of course, X union Y E is K regular with K greater than 1, then G has a one factor, which is same as telling that G has a perfect matching. Okay, so, I believe that you remember what is K regular graph. K regular graph means every vertex is having degree K. So, if a bipartite graph is K regular, that means the number of vertices in both parts are the same, right. So, here is an example of say a 2 regular bipartite graph. So, every vertex has degree 2. So, this is degree 2 now. Okay. Yes. So, this is a 2 regular bipartite graph. And if this is the x side and this is the y side, then we know that the degree sum in the left side d of v belongs to x is equal to, the degree sum will be the same, right, d of v belongs to y, and since all the degrees are same, say k here, and here also all the degrees are k, then and this sum is cardinality of y into k, and this sum is cardinality of x into k. So, these two are equal. So, x has to be equal to y. I mean x has to be equal to y means the cardinality of x has to be equal to the cardinality of y. So, now let us prove this theorem that a k regular graph, bipartite graph, has a perfect matching. So, as I stated here, as G is k regular, then obviously the cardinality of x is equal to the cardinality of y. Thus, it is sufficient to prove that G has a X saturated matching. Since the cardinality of X is equal to the cardinality of Y, so if the graph is having this bipartite graph, if it is having a X saturated matching, then that is the perfect matching, because it will also match all the vertices in the Y side. Now, a graph will have X saturated matching if and only if the Hall's conditions are true. So, what I have to prove is that you take any, so we need to prove the Hall conditions, that we need to prove that that the cardinality of the neighbor of S is greater than or equal to the cardinality of S for all S subset of X. Okay. Let do it for an arbitrary subset, say S be an arbitrary subset of X, and let M be the number of edges from S to N S. Now, what is M? Since this G is K regular, every vertex in S has degree 3, right. So, the number of edges that is going from S to N S is 3 times the cardinality of S. So, this is the number of vertices in S, sorry, not 3 times, it is K times, it is K times the number of cardinality of S. So, this is the number of edges that is going from S to N S. So, these M edges are incident to N S. Now, see that the vertices in N S, they are also of degree K. Now, so this N S, the cardinality of N S can't be less than the cardinality of X, because this many edges are going to N S, and suppose N S has cardinality of N S many vertices, and so that in terms of the number of vertices going out of N S, that is this much, and this must be greater than or equal to this one, because suppose here is your X and here is your say S, and this is your Y and this is your say N S. So, all the M edges, they are all going to N S only, but some edges of N S are going outside S also, right. So, the number of edges going out of N S, that is greater than or equal to the number of edges, this one. Okay, so, the cardinality of N S is this implies that the cardinality of S is less than equal to the cardinality of N S. So, Hall's conditions all conditions are true. So, G has X saturated matching, which is also a perfect matching. Perfect matching. So, perfect matching is also called one factor. So, this part is slightly tricky, but I hope that you understood because yeah. So, see the every vertex in NS are also of degree k, right. So, this and what I explained here, some of the edges are going out of, not all the edges from NS are going to S, they might go outside S. So, this condition is true. Okay. So, what we proved is that if a graph, a k regular bipartite graph has perfect matching. So, that is all in the first part of 8th lecture. Thank you very much.